When you're writing equations for reactions that happen in solution, typically aqueous or water-based solutions, you have a couple of different options for the form of the equation. You can write molecular, total ionic, or net ionic equations. Specifically, when you're having a reaction between ionic species, or at the very least strong electrolytes, what you can do is you can write a metathesis reaction. So if you have two examples, HCl and NaOH, HCl is a strong electrolyte, NaOH is a strong electrolyte. When they react, what they do is they switch their cations and anions. And you can write HCl plus NaOH goes to NaCl and HOH. And HOH we will generally rewrite as H2O. When you're writing reactions, when you're writing equations, what you should do is you should include states of matter. Since these are happening in solution, the states of matter are aqueous. HCl is dissolved in water to make an HCl solution. NaOH is dissolved in water to make the solution. The solution is where the reaction is happening, so the NaCl is aqueous, and water is not aqueous, it's a liquid. And what we do is we confirm that all of these things are in fact aqueous and nothing is precipitated by looking at our solubility guidelines. We look at Cl-. Cl- is on the top part of the chart. It's always soluble, so HCl is soluble. NaOH, the OH- is always insoluble. It's on the bottom of the chart. But the alkali metal cations are one of the exceptions, and sodium ions are alkali metal cations, so they are aqueous. We look on the right-hand side of that reaction arrow, and sodium ions and chloride ions are generally always soluble, so it's aqueous. Water, of course, is a liquid. This is a molecular equation. The total ionic equation is where we take all of the strong electrolytes and we split them up into their ions so that we have a good idea of what's exactly happening in that solution. If you had a bucket filled with water and you dumped in some HCl and NaOH, the ions would be formed. H+ ions, Cl- ions, Na+ and OH- ions. And they would all be floating around in solution. They would be the things that react. So you would have H+ and Cl- and Na+ and OH-, all aqueous. And they would all react to produce sodium ions and chloride ions, again both aqueous, and they would produce H2O liquid. And this represents your total ionic equation. All of the things that can be split into ions have been split into ions. And all of the things that cannot be, like H2O, are left as is. And the net ionic equation is built from the total ionic equation. You take the total ionic equation and you subtract anything that shows up on both sides. You cancel them out. And then what you're left with are ions on one side and a non-ionic species on the other side. So it basically simplifies the thing so that you only end up with the components that are actually undergoing any sort of reaction. In this example, the chloride ions show up on either side of the total ionic equation. That chloride ion just floats around in solution and it never actually does anything. The sodium ions are the same way. They show up on both sides of the equation and they don't actually do anything. So when you cancel them out, what you're left with is the net ionic equation. You have aqueous hydrogen ions reacting with aqueous hydroxide ions, and they react to produce water, which is a liquid. And you're left with a net ionic equation. Generally, these things are produced because they simplify things and they make it a little easier to see what's actually reacting. Our second example is the reaction of aqueous sodium carbonate with aqueous barium acetate. Our molecular equation is calculated the exact same way as our previous example. You just do a metathesis reaction where you switch the cations and anions. So what we do is we write 2 sodium acetates and 1 barium carbonate. And we need to include our states of matter, aqueous, 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 and solid. And the way we determine whether or not things are aqueous or solid is exactly the same as we did in our previous example, where we use our solubility chart. Carbonate ions are always insoluble, they always precipitate, unless the cation is an alkali metal ion or the ammonium ion. In this case, sodium ions are alkali metals, so they are always going to be soluble. So sodium carbonate is aqueous. Barium acetate contains the acetate ion, which is always soluble with no exceptions. And sodium acetate also contains that acetate ion, always soluble with no exceptions. So our first three components are all aqueous. Our final example of barium carbonate contains carbonate ions, which are always insoluble, and barium is not one of the exceptions, so it's a solid. So this is a precipitation reaction where we have barium ions and carbonate ions reacting to produce barium carbonate. Our total ionic equation is prepared by splitting all the strong electrolytes into their ions. Basically anything that is ionic and soluble is a strong electrolyte. So we have 2 sodium ions plus a carbonate ion from the sodium carbonate splitting into solution. I'm going to leave out the states of matter for anything that's aqueous and ionic. Generally speaking, at least in this class, anything that's ionic, anything that is an ion rather, will always be aqueous. We'll assume it's reacting in water. So sodium ions will always be aqueous, carbonate ions always aqueous. Then we have barium acetate, which is barium ions, barium 2+, and 2 acetate ions. And again, I'm leaving out the subscripts for the states. Ions are always going to be aqueous. And this goes to 2 sodium ions and 2 acetate ions and barium carbonate. Barium carbonate is a solid. So we have our total ionic equation. Everything that can split up has split up. And our net ionic equation is calculated exactly the same way as it was in the previous example, where we cancel things that show up on both sides. 2 sodium ions, they cancel. 2 acetates, and they cancel, so we're left with CO3 2- plus Ba2 plus, all going towards BaCO3 solid. So this is our net ionic equation where we have ions on one side and a solid, or at the very least non-aqueous system on the right-hand side. In this case, we have a precipitation reaction where a solution of carbonate ions and a solution of barium ions react to produce solid barium carbonate.